Alright guys, welcome to this video. In this video we are starting chapter 4, which is integration. Okay, so the another name of integration is antiderivative, so which is just the opposite of the derivative. For example, do you remember that what is the notation for the derivative? There were several notations for the derivative, but one of the notation was d over dx, right? So d over dx of x to the cubed is how much? Do you remember that? Just use the power rule, n and then x and minus 1, that is 3x squared. We did that way, right? So basically the notation for the derivative here is d over dx. So for the antiderivative, we use a notation like this is the integral sign, and then that comes with dx. Okay, the function will come here in the middle. So this is like integral sign, or the antiderivative sign is like s type of thing, and then there is a dx that comes at the end. All right guys, so let's see some examples. So the derivative of x squared, it is like d over dx x squared is derivative of x squared, because this is the notation for derivative, d over dx. You cannot cancel d and d. So that's the notation for the derivative of x squared is 2x. So what can we say is the antiderivative of 2x must be x squared. It's just the opposite, okay? The antiderivative is the opposite. So the integration of 2x, or antiderivative of the 2x, you see that? We wrote s symbol and then dx here, right? So integral of that thing is x squared. But you see that why I wrote x squared plus c? I will discuss about that. Look at this. The derivative of x squared is 2x, right? Similarly, what is the derivative of x squared plus 5? So it is also 2x, right? So the antiderivative of 2x can be just x squared, or x squared plus 5, or x squared minus 1, because the derivative of x squared minus 1 is also 2x, right? So what is the antiderivative of 2x then? Antiderivative of 2x can be x squared, or x squared plus 5, or x squared minus 1, or x squared plus or minus any number, right? That's why we wrote the antiderivative of 2x dx is x squared plus a number c. That c can be 0 or 1, 2, 3 or negative 1, 2, 3, anything there, or just a number. That's why we write that. Now what I did both sides is I divided by 2 on both sides. What we get is antiderivative of x dx is x squared plus 2 plus another constant. So this was c, I assume that as c. So I assume that as c prime, because I divided both sides by 2, right? I did like 2 and then 2 and then 2. So I denoted the new constant by c prime. But you can just write c, that c is different from that c. You can take that way. But this is how we got the antiderivative of x dx is x squared over 2 plus a constant c prime. Similarly, what is the antiderivative of, what is the derivative of x cubed? The derivative of x cubed is 3x, 3 minus 1, that is 3x squared, right? So what we can say there is the antiderivative of 3x squared will be x cubed plus c. The antiderivative of this must be that one, right? So what we can say from here is basically, if you divide both sides by 3, you will get the antiderivative of x squared, or the integral of x squared dx equals to, I divided both sides by 3, x cubed over 3 plus c. You remember that how I got c? Because the derivative of x cubed is 3x squared. Derivative of, if you say x cubed minus 1 is also 3x squared. If you find the derivative of x cubed plus 10, this is also 3x squared, right? All of them have the same derivative, right? That's why the antiderivative of 3x squared could be x cubed, or x cubed minus 1, or x cubed plus 10. That is the reason why I wrote c, as we discussed for x squared, right? So the antiderivative of x cubed dx, x squared dx is x cubed over 3 plus c. Now from this, can you guess? So look at this one. If the exponent is 1, then the antiderivative will be exponent plus 1, that is 2, divided by what exponent you got here, that will go in the denominator. You see that? Similarly here, when the exponent is 2, the antiderivative of x squared is x cubed over 3. You can think like the whatever exponent there plus 1 over that thing plus 1, right? The exponent plus 1. So basically, it's like a power rule, but it increases the power. In the derivative, it decreases the exponent, right? But here it increases in the antiderivative, because that is the opposite of the derivative. Okay, so you see, for the derivative, that power goes to the first, and then you write x and then 1 less, right? But here, you increase the power by 1 and divide by that power. We don't multiply, we divide by that power. So can you tell me what is the antiderivative of x cubed? So you see that the antiderivative of x cubed is, you should write x to the 3 plus 1, the power plus 1 over 3 plus 1 and then plus c. This plus a constant is default in the antiderivative because you always write that for any antiderivative problem, you write plus c, okay? But here it is x to the third, means x to the third plus 1, the antiderivative over 3 plus 1. That is, what you get is basically x to the 4 over 4 plus 1. That's what you get. How about x to the fourth, antiderivative of x to the fourth? Can you tell me the final answer? Yes, you're right. X to the 5 over 5 plus 1. So who can tell me what is the antiderivative of 1? There is no x to the exponent, right? So you can write 1 as x to the 0, right? Anything to the 0 except 0. Any number to the 0 or any variable to the 0 is 1. So you can write that way. So you use the same formula. 0 plus 1, x to the 0 plus 1 over 0 plus 1 plus c, right? So what do you get? X to the 0 plus 1 is just x to the 1, is just x over 1 is just x, right? So you get x plus c. You remember, you can see the other way. You can check your answer, okay? How do I check my answer then? To check whether the antiderivative of x cubed is x to the 4 over 4 plus c, not 1, plus c is a right answer or not, what you do is find the derivative of this. You must get that function, okay? What is the derivative of x to the 4 over 4? You don't have to use quotient rule here. Just pull the 1/4 out. And the derivative of 4 will be, x to the 4th will be 4x to the 4 minus 1. 4x cubed. And you cancel 4 and 4. Basically, you get x cubed. And the derivative of constant is 0. C is 0. Similarly here, the derivative of this is 5x to the 4th divided by 5. That is 5 and 5 will cancel out. So x to the 4th, this is also c. And so x to the 4th plus the derivative of c is 0 here. So what do you get? X plus c, right? What is the derivative of x plus c? Derivative of x is 1, derivative of c is 0. So just 1. That's how you can check. So these are some of the formula that we get. So can you tell me what is the derivative of 0? You can think this way. What is the function whose derivative is 0? A number, right? A number has derivative 0. That's why integral of 0 is a number. Let's say c. So integral of 0 is c. The derivative of c is 0. It's just the opposite. So can you guess what is the integral of k? You can write like this. You can pull that k out and then do 1 dx. But what is the integral of 1? It's x plus c, right? So you can do k and then x plus c, right? Basically, you can simplify this as k times x is kx plus k times c. K is a constant, c is a constant, so you get another constant, let's say c prime. So basically, the integral of k, integral of a constant is constant times x plus a constant. You can write c or c prime. So we just did for the next formula, we did that, right? So if there is any exponent n in the integral, when n is not equals to 1, n cannot be equals to negative 1. If n is negative 1, then n goes to the denominator, right? And then that will get a problem here. So suppose n is not equals to negative 1. Okay, we will see other things why n cannot be equals to negative 1. So what is the antiderivative of that? It is x to the n plus 1 over n plus 1 plus c. You see that? We got that everything here. X to the 1 has x squared over 2. X to the 2 has x cubed over 3. And then x to the 3 has x4 over 4. X to the 4 has x5 over 4. x5 over 5 and so on. That's why x to the n, where n is not equals to negative 1. Okay, it cannot be equals to negative 1. Why? If n is negative 1, then you will get negative 1 plus 1 is 0 there, right? So which gives you infinity. That's why n cannot be equals to negative 1. So what is the antiderivative of cosine x? Tell me, whose derivative is cosine x? We know that derivative of sine x is cosine x, right? So what is the antiderivative of cosine? Antiderivative of cosine must be sine, right? So similarly, what is the derivative of cosine x? Cosine of x derivative is sine x, right? Negative sine x. So the antiderivative of sine x will be negative cosine x, like that. So it will be, the antiderivative of cosine x will be sine x plus c. You see that? Because the derivative of sine will be cosine and derivative of c is 0. Similarly, this will be negative cosine of x plus c. Why? Because the derivative of negative cosine is positive sine. So who remembers what is the derivative of, which derivative is secant squared? You're right, the derivative of tangent x plus c is secant squared. How about secant tangent? Derivative of secant x plus c is secant tangent. That's why the antiderivative of secant squared is tangent. Antiderivative, oh, I forgot dx here. I need to write that dx here. So antiderivative of secant x tangent x is just secant x. Which derivative is cosecant square x? That is negative cotangent x plus c. So the derivative of negative cotangent is positive cosecant square. That's why the integral of cosecant square x is negative cotangent x plus c. Similarly, this is negative cosecant x plus c, and these two are just for the general function. If there is sum in the integral, you can distribute that integral. See, there is fx plus gx inside the bracket there. What I did is I assigned the integral and then dx to fx, and the integral plus in the middle. You see that? That is the plus. We had the plus here. And then integral of gx, dx. Integral and the antiderivative are the same thing, okay? Now the last one is, if there is k or constant number times a function, then you can pull that out and then find the integral of constant only. So these are the formula, that the basic formula that we will be using in the examples.